Okay. Okay, hi everyone. So let's get started. So let me introduce our speaker. Professor Onur Mutlu is a professor of computer science at ETH Zurich. Previously, he held a distinguished named professorship at CMU. His research interests are very broad, but currently they're in computer architecture, systems, hardware security, and bioinformatics. Onur's research is highly impactful. For example, the techniques have influenced industry and have been employed in commercial microprocessors and memory and storage systems. And also, he pretty much started the whole RowHammer research topic back in 2014, which has been very popular since then, pursued by many researchers in both industry and academia in many different communities. So we will hear more about RowHammer today. Onur is an ACM fellow, IEEE fellow, and an elected member of the Academy of Europe. He has many, many awards, too many to read here, but you can always read his bio. I'll just mention that just this week at Micro, Onur and his student won one of the best paper awards. And Onur is also currently the #1 author who has the most number of papers in Micro. And I don't know if other conferences have this kind of ranking, but I'm sure he's up there as well. One more interesting fact about Onur, he is a YouTuber. He actually publishes his lecture videos and he keeps updating them as well. So I would definitely recommend you to check out his YouTube channel if you want to learn more about computer architecture. So with that, let's welcome Onur.
Hey, thank you very much, Yanjing, for the kind introduction. I should probably say that I'm a YouTuber, but I don't make money on YouTube. Maybe that's a good alternative choice career to follow in the future. Yeah, different. Yeah, exactly. No money for me, at least. For YouTube, probably it makes money though. Okay, so thanks for coming to this talk. I'm going to talk about the story of RowHammer, something that we have been working on for about a little bit over a decade right now. I find this fascinating because this is connecting reliability issues with security issues, in my opinion. And I start, when I teach about RowHammer to freshmen, I use the example of this bridge. This is the Tacoma Narrows Bridge, which doesn't exist because a bit flip happened in it, and this is what happened to it. Later, they built 2 bridges over there. That's a fundamental redundancy principle, right? You have dual modular redundancy. I also use this picture. These folks are constructing a big city, and they're very happy now. But if a bit flip happens on that road that they're sitting in, they will not be happy immediately. So I think of security in a very general perspective. We should really be thinking of security, in my opinion, as preventing unforeseen consequences. You can criticize us as being very vague, but we're going to deal with systems that we design that are going to be out there, that are going to be making decisions for us, that are going to be driving us. Like this, perhaps. This is Mr. Bean, of course. This is from 1994, self-driving car. But if you get bit flips or security or safety issues over here, maybe you should really be thinking about unforeseen consequences that you didn't think of when you were training the neural networks that are going to make decisions for you going into the future. So what is RowHammer and what is its relationship with? Essentially, RowHammer is the bit flip that causes these security, reliability, safety issues. And it's the fact that you can predictably induce bit flips in commodity DRAM chips today. And at the time we first did the studies on RowHammer in around 2012, we found out that more than 80% of the tested DRAM chips are vulnerable. I'm going to show you more recent data from 2020, 2022 that shows essentially this is still true, and it's getting worse. And as far as I know, this is the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. If you know something else, please let me know. We're going to get back to this at the very end of the talk about some security works that happened before RowHammer. And I like this sort of article that people are writing. Forget software, now hackers are exploiting physics. This is a nice high level thinking about RowHammer. It's really a physical problem, the device level problem that affects essentially everything up the stack. And I'm going to give you a little bit of how we arrived at this before I go into more details on RowHammer. So we were working on memory technology scaling issues. And this is one of the papers that were invited that we wrote to International Memory Workshop, which is essentially an industry dominated workshop. They were interested in what is the future of technology scaling. And here we argued that technology scaling is going to get worse. We're going to have a lot more reliability, safety issues. At the time, we were working on RowHammer, but we didn't publish our first paper. And our argument was we should really be taking a systems approach to actually fixing these issues that we're going to see with technology scaling. And what are these technology scaling issues? We were mainly focused on main memory. And RowHammer is something that affects main memory. If you look at main memory, today's main memory is all DRAM. Dynamic random access memory, and it's going to be there for some time, I believe. DRAM stores charge in the capacitor, and data is encoded based on the charge level in the capacitor, whether charge is present or absent based on some threshold. And this capacitor must be large enough for reliable sensing. And this, there's also access circuitry, access transistor, bitline, and sense amplifiers. And the access transistor and the access circuitry must be large enough for, again, reliable sensing, low leakage, high retention time. So for this circuit to operate, both of these properties must remain true. Now, unfortunately, as you reduce the size of the circuit, size of every structure over here you see reduces. As a result, you're much more vulnerable to reliability issues and noise issues. And RowHammer is one particular noise issue. It's read disturbance in particular that gets much worse as you reduce the size of everything that you see in this picture. Okay, so I'm going to give you the story of how we arrived at it. So we were doing a lot of studies together. This is one study with Facebook that we did on their data centers, all of their data centers in the entire world. We wanted to understand the effect of memory errors in systems. And if you look at this figure, this is an average across all of the memory that we tested, which is a lot. This is in production data center. So we collect this data while the applications are running in the system. And you see a correlation, basically. This is the DRAM chip density employed in the system and the server failure rate normalized to some other metric, basically, which you can read about in the paper, or I'm happy to talk about. But the key takeaway is, if you employ a dense DRAM chip in your system, you get a high error rate. And this has system level implications that we discuss in the paper, which I'm not going to go into, which is also fascinating, but that's not the subject of what we're dealing with. If you're interested, the paper has a lot more data over here. So this is a large scale study. You cannot really identify a lot of things. You cannot pinpoint things because you don't have control in a production data center. So what we later decided to do is understand these effects in a small scale. And we built these FPGA-based DRAM testing infrastructures where we had memory controllers that we built, and we could test DRAM chips using these memory controllers. And we were interested in many, many things in DRAM. I'm going to mention one particular thing, which is retention time. We did a lot of work on retention time, and we're going to get back to it toward the end of the talk because there's a very interesting relationship between retention and RowHammer as well. So this is one of the infrastructures where we did a lot of our RowHammer studies on. And we open source this infrastructure so that the community can use it. It's actually very nicely programmable. There's a C++ API. It's used by industry and academia. Actually, there was a paper at Micro this year that used this infrastructure to show that you can actually have fractional values in DRAM. I think people should build on that idea to come up with other stuff. So I'm happy that this is open source. We're going to release a new version of it that's even more easy to program. We are hiding the FPGA from people. We can program the FPGA using Python and test your DRAM chips if you're interested. We're happy to support it, basically. So why did we build this infrastructure? We wanted to understand these DRAM scaling issues. And at the time, initially, at least what I thought was the real scaling issue is refresh, meaning you have this charge-based memory, and this charge becomes smaller and smaller as you make this the capacitor small. As a result, you need to refresh the circuitry because this charge leaks. And I believed at the time, and the data also suggested at the time that this retention is going to get much worse. And it is getting worse, no question about that. But it turns out RowHammer is even worse. I didn't believe that at the time, but I believe it's true at this time. Basically, the reason we built this infrastructure was to get rid of refresh as much as possible so that we can get rid of this big scaling issue. And there's multiple ways of doing this. By building this infrastructure, you can characterize the DRAM chips, characterize the DRAM cells, and figure out how long they can retain data before data corruption occurs. And this is a very common picture you get in DRAM chips. Most of the cells can retain data by more than 250 milliseconds. Very small fraction of the cells can retain data between this interval. But at the time, we were refreshing DRAM cells every 64 milliseconds. Now, if you look at this picture, you can start developing techniques. Oh, why do we refresh everything every 64 milliseconds, right? You can develop many, many techniques across the stack, and we did some of that. Other people did some other of that. This is not an easy problem because these retention times are dependent on the location of the cell, they depend on the data value, and depend on time. There are some quantum-like effects that actually randomly change the retention time of the cell. So we developed a lot of techniques to overcome that, and other people also developed them. I'm not going to talk about them. So the infrastructure enabled us to do a lot of studies. I still find these very, very fascinating, actually. If you're interested, we're happy to support research in this direction. So you can see that we've been working on this even recently. Okay, that's refresh. And this is the enabling infrastructure to do those studies. So while we were doing those studies, we were also building infrastructures with flash memory that I'm going to show you later. And flash memory has a lot of reliability problems also. One of the reliability problems is disturbance issues. Whenever you read a page in flash memory, you disturb all of the other pages in the same block. So we asked the question, does a similar phenomenon actually exist in DRAM as well? And we did studies together with Intel, starting from 2012, and we found out essentially it does. Basically, you can predictably induce errors in most DRAM memory chips. This is now known as the DRAM RowHammer phenomenon. I already mentioned these to you. So what is the problem, basically? The problem is read disturbance. Whenever you're reading a row, you're disturbing physically adjacent rows. So in DRAM, if you want to read some data from some row, you need to activate that row, which means I need to apply high voltage to that word line. This is called opening the row or activating the row. Now, if you want to read some other row, you need to close this row by applying low voltage. Now, if you keep doing this repeatedly, the second applying low voltage is called pre-charge. Now, if you keep doing this repeatedly, high voltage, low voltage, activate pre-charge, activate pre-charge, activate pre-charge, it turns out because of the disturbance that you cause of this word line toggling, some physically adjacent cells and physically adjacent rows flip. They lose their charge and they get corrupted basically. Clearly, this should not be happening, right? You're not even writing to any place in memory, including this row. You're not touching any of the rows. These rows are corrupted. So we call the hammer row, we call the victim rows. And clearly, these rows can belong to your application. It could belong to the operating system. It could belong to some other application. It doesn't matter. You should not be doing this basically. This breaks memory isolation. And we show that more than 80% of the chips that we tested that belong to 3 major manufacturers, there are only 3 major manufacturers in the world in DRAM, were vulnerable to this effect. And this is a technology scaling problem. Basically, the chips that were manufactured before 2010 did not have this problem. You could argue that we didn't do good enough testing, and that's absolutely true. But as you go backwards in time, this problem doesn't occur. This problem started occurring in 2010, and all the chips that we tested between 2012 and 2013, manufactured during that time, were vulnerable. So why? Because we need to do enough activates so that we can beat enough charge from these vulnerable cells. And around 2010, you were able to do enough activates to cause this effect. So the number of activates to cause this effect started reducing over time because the cells became smaller, they're not making enough charge, and the cells are closer to each other. And this is getting worse, as we will see. So at the high level, why is this happening? DRAM cells are too close to each other, they're too small, they're not electrically isolated from each other. Access to one cell affects data in nearby cells due to electrical interference between the cells, as well as the wires and the cells. This is also called cell-to-cell coupling and interference. There are multiple device-level reasons that affect this. I'm not going to go into that abstraction level. I'm going to draw the abstraction level here. And I like this abstraction level because you can think of it this way. When you activate or apply high voltage to a row, an adjacent row gets slightly activated as well. And vulnerable cells in this slightly activated row drain their charge, slightly lose a little bit of charge. If RowHammer happens enough times, if you do this enough times, those vulnerable cells lose their charge enough that their values corrupt, assuming you don't refresh them in the meantime. So clearly, one way of solving this is increasing the refresh rate. Right? You refresh things much more frequently so that you cannot do enough activates within a refresh interval that would cause the RowHammer problem. But we will see that that's a very bad solution. So this is where RowHammer and refresh ties together. That's why what I showed you earlier is not useless, let's say. Okay, so higher level implications, basically this is a device level issue. It really affects everything upstream, let's say, including the user. So why? Because you can actually induce these bit flips using a user level program like this. We actually open sourced this code at the time. Google later improved it. You could actually get rid of the M-fence over here. But basically what this program does, it selects addresses X and Y so that they map to the same bank. And it basically avoids caches to those rows and avoids the row hits. It does this, ping pongs activates to X and Y. Okay. And if the chip is vulnerable, you get bit flips. Now, we also observed in the paper that if X is here and there's one row sandwiched between X and Y, you get even more bit flips. This is called double-sided hammering. Google later actually perfected this and made it much stronger. At the time, we did our experiment with single-sided hammering and showed that the issue is bad. Google showed that it's even worse. Okay, so this is a user-level program, remember that. And this is the effect that we saw in the real systems that we tested at the time in our original paper. So real systems are vulnerable, clearly. But there's nothing special about Intel and AMD because all memory controllers today are capable of doing these activates within a refresh interval. So one can actually take over an otherwise secure system using this because a user-level program can induce these bit flips reliably and break memory isolation. When we wrote the paper, we said memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. I think this is very fundamental. We should not break this memory isolation at the hardware level. And we said that we didn't do this, but we said that someone can hijack your computer using these bit flips. And while we were looking into it, these very smart folks from Google Project Zero did exactly that thing that we were interested in. They basically showed that they could take over the system by exploiting RowHammer. Now, I'm not going to go into the details. This is beautiful security engineering. This is copy and paste directly from their blog post. They also have a beautiful black hat presentation. Mark Seaborn has it. Thomas Dolian also delivered talks on it. But basically, they replicated the problem based on our paper. They showed that they could build 2 working privilege escalation exploits. One is not so interesting to me, at least. It takes over the Google native client. The other is very, very interesting because it takes over the Linux kernel as a user-level program. This user-level program flips the right bits with enough security engineering that it gains access to its own page table entry that points to its own page table. Basically, you gain write access to your own page table by doing good enough security engineering. How do you do that? I don't have enough time to talk about it. Take a look at what Google did. And their other works actually did other stuff later on. So as a result, they compromised the system. And this became very interesting to people as RowHammer vulnerability. They start drawing pictures like this, not my pictures, but nice pictures. I like them. A famous hacker on the internet said, RowHammer is like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you're after. So if RowHammer effect is true in this room, if you're locked, don't worry. Keep banging on the walls, the door will magically open. Yeah. That's a joke, of course. don't try it, maybe. Okay, so, but this bit flip actually can be exploited in many ways. Yes, please. There you go. RowHammer was true over there, apparently. I like that. Yeah. So this bit flip was exploited in very creative ways by the security community. Now you have a software inducible bit flip, and people showed that they can gain unrestricted access to systems of website visitors. This is beautiful work. These people showed that you can actually take over the Android phone deterministically. Again, I don't have time to go over it, but these are very beautiful works. These folks show that you can accelerate these attacks using the GPU, using the WebGL interface. These folks show that you could do this attack over the remote direct memory access interface. These folks show that something similar. These folks show that even if you're not able to gain access, you can leak private data that you're basically, you can break confidentiality. That's another interesting direction for sure. And more recently, people have been looking at deep neural networks, and they've been showing that if you induce bit flips with RowHammer in a reasonable way, you could actually tank the accuracy of these networks. Otherwise, a very accurate network may be quite inaccurate, basically, due to RowHammer. There are actually more works that I don't have time to go over here. So maybe this is a solution, right? Your computer's broken, why not solve? This is another picture that I don't have. I don't think this is a solution. So there's a lot in RowHammer that I'm not going to cover. We were invited to write this paper on this hardware security issue of TCAT. We cover a lot of work in this area from the device level all the way to upper layer systems levels. If you're interested, this is a nice survey. Unfortunately, it's not it's a bit out of date. It covers all the work. It's not going to cover what I'm going to cover later on. Before we go into the recent works, let's talk about understanding of it, because I think if you want to solve a problem, you really need to understand it. And in our first paper, we actually built a lot of understanding based on the experiments. So we analyzed many DRAM modules, and we built some understanding. I'm going to give you some basics very quickly. So the first question is, what is the difference in terms of row addresses between the hammered row and the victim rows from the perspective of the memory controller? From the perspective of the memory controller, most of them are adjacent. There's a one difference, but some of them are not adjacent. Now the question is, what does that mean? Well, according to us, this means that there's some internal remapping of the rows internally in the DRAM chip that the memory controller is not aware of. And this happens because of various reasons, because you want to get rid of some faults inside the DRAM chip. So the takeaway here is, if you want to solve this problem at the memory controller, you do not know which addresses are adjacent based on your address space. So you need to reverse engineer something, or better yet, someone communicates this information to you, which good luck with that, because no one in the DRAM industry is going to tell you what addresses are adjacent to each other inside their DRAM chips. Okay, this is one challenge we will see later on. The other question is, how fast can you activate rows, and what is the effect of that on the error rate? So this is not allowed according to the standard. If you activate at the maximum rate allowed by the standard, you get the most errors, as you can see on this. And if you reduce your activation rates, clearly error rate reduces. But that's not necessarily a viable solution, because if you need to reduce your activation rates to very, let's say, unreasonable latencies, so that you can get rid of every single error. So you don't want to do it in a naive way, let's say. As we discussed, refresh interval affects things. At the time, chips were refreshed every 64 milliseconds. Today, that came down to 32 milliseconds, by the way. So refresh is getting worse over time. So if you actually make the refresh interval smaller, make the refreshes more frequent, you can get rid of errors, as you can see. And if you want to get rid of every single error that we saw, you need to make your refreshes 7x frequent. Clearly, that's not tolerable, because that increased the performance degradation, as well as quality of service degradation, as well as energy in your system. So we have a dilemma here. Refresh is a scaling problem. We want to get rid of refresh as much as possible. RowHammer is another technology scaling problem. RowHammer can be fixed with refreshing more. So DRAM scaling is difficult. One of the reasons is this, basically. So data pattern is very interesting. So some data patterns are much worse in terms of inducing errors because they cause much more coupling, cell-to-cell coupling. Okay. So there are other results in the paper that I'm not going to talk about in detail, but this leads to the security problem. Errors are repeatable. ECC cannot correct the errors because you get a lot of errors per cache line. We're going to get back to that also. And you can do double-side hammering, as we discussed. If you want to know more about the initial results, this is the initial paper. I'm going to talk about these things in 2020 and more recently. Basically, things are getting worse. And there are a lot of other effects that we did not study in the initial paper. We're going to talk about that. And there are some other effects also that we did not study. And I believe there are other effects that we did not study yet. We're studying right now. And if you people are interested in studying, you can actually do those experiments using FPGA-based infrastructure. Before I go into it, let me talk about solutions, especially at the time. So if you want to solve a problem like this, you need to develop two types of solutions. One is immediate solutions, because there are chips out in the field that are vulnerable, right? What do you do about that? Clearly, you have limited possibilities there. And the second is longer term, which you can actually exercise your creativity more. So we propose both types of solutions, and I'm going to talk about some of them. So making better DRAM chips is not easy, actually. We can discuss that, but this is very tough. Manufacturers are trying to do that. They're reducing the effect of RowHammer as much as they can. Still, RowHammer is present. Refreshing frequently, as I said, is not a good idea in my opinion. ECC, I also believe it's not a good idea, and we show that you can bypass the ECC. Other works have shown that they can bypass the ECC, and I believe ECC is a very bad solution for this because error correcting codes are very good if you do not know the cause of the error, right? If you have random errors, for example, error correcting codes are great because you're protecting everything. But here we know the cause of the error. Maybe we can do something much better, much more specialized. At the time we wrote the paper, we didn't believe access counters would be that interesting because of the overheads. Now we've actually reversed our position on that based on the data that we've obtained. I think this is more and more interesting today. Figuring out which rows are being hammered using some access counters or Bloom filters or some type of mechanism, and try to either block those rows from being activated or refresh victim rows. We're going to get back to that. What was the immediate solution that was employed by industry? Essentially increasing memory refresh rates. This is Apple's security release. They basically said they mitigated the RowHammer problem. They acknowledged the problem, actually. Apple was one of the first companies to acknowledge the problem clearly in their security release. And they basically said we mitigated this problem by increasing memory refresh rates. They didn't say by how much. I believe by 2x. But 2x is not enough to get rid of. They closed the vulnerability base. And they were nice enough to cite our paper also, saying that they worked around that. But the industry, this is across the industry base. Everybody increased the memory refresh rates for this. So our solution, which I believe has a very good idea to begin with, at the time was probabilistic adjacent row activation. Basically, the idea is memory controller, after it closes the row, it activates adjacent rows with very low probability. This refreshes the adjacent rows, so it replenishes the charge in them. And if you do it probabilistically, you don't incur a lot of overhead. And with this sort of probability, we get very good reliability guarantees. And if you're paranoid, you can adjust the value of P to be higher and pay the performance energy cost. Now, this solution is stateless, low cost, low complexity, low performance overhead. We believe this was a good solution. And actually, it could be implemented in the DRAM chip, it could be implemented in the memory controller, and you've seen implementations on both in real systems. We're going to get back to pair, but this is Intel's implementation, for example. Intel implemented their memory controllers before DRAM manufacturers said they solved the problem. But you could, for example, choose 2x refresh or hardware RowHammer protection, and hardware RowHammer protection is a version of probabilistic adjacent row activation. It's not exactly what we envisioned, but it's a step in the right direction, in my opinion, because we didn't envision this to be biased, programmable. We thought this would be more dynamic. Memory controller would do it itself without exposing it to the user. Okay, so basically, I think my takeaway, which we're going to review first later, is you need intelligent controllers to solve this sort of issues. And intelligent controller can be implemented in the memory controller or inside the DRAM chip. And flash memory has intelligent controls. This was the flash infrastructure that I talked about that we were working on. And we did a lot of work in this flash infrastructure. And this has an intelligent controller, actually. SSDs have intelligent controllers to overcome a lot of these issues like read disturbance. I don't have time to talk about this, but I find this also fascinating. If you're interested, you can look into it or talk to me. Okay, now let me talk about what we did more recently, 2020, 2022, and what others also did more recently. Are there any questions before I move on? Yes, please.
Is there any accidental?
Is there what, RowHammer?
Accidental.
Oh, okay, that's a great question. Basically, do benign applications that are not attacks exercise cause bit flips? Now, I believe today that's much more likely. at the time we were doing these studies, the number of activates you needed to do to actually induce a bit flip was on the order of 100,000. Now, if you do double-sided RowHammer, you could reduce it to 50,000 or so. Anecdotally, we learned that there were some applications that would do this, especially if they had uncacheable accesses and they had locking in the memory controller, etc. But we didn't observe it. But anecdotally, yes, the probability is extremely low. With today's thresholds, the probability is a bit higher. And we're going to talk about that later on. Yes, please.
So not RowHammer specifically, but wouldn't you say that the increased failure statistics you saw for the higher density memory would account for some effect like this?
So that's a good question, basically. What fraction of the increased failure rates are potentially due to RowHammer? And the answer is I don't know, because it's very difficult to isolate those studies. Now, when I talk to industry folks, they hint that RowHammer is a good fraction of it, but they cannot speak as to how much of it. Yeah, I would love to do that study though, if we can isolate it. Okay, one more.
Level mitigations that you could do, like,
Yeah. So we're going to talk about mitigations, and the answer is yes. Potentially, you can isolate security critical pages. You can space things further. Usually, those lead to higher memory overheads. And potentially, you could use performance counters. There were solutions proposed, basically. Either they lead to very high overheads in terms of memory, or they're not fully secure. And these were shown in prior works.
you sort of break the abstraction also. Yeah, it's complicated.
Yeah, I mean, if you can do it, that's great. The problem is today's, as I will show you in a little bit, the number of activations you need to do to induce a bit flip is getting lower and lower. Soon we're going to see 1,000, maybe 500. Okay, these are good questions. So basically, we wanted to revisit RowHammer after 6 years or so. So we want to do a scaling study as to how things are going, let's say. Part of the reason was DRAM manufacturers claimed that they solved the problem. They basically solved the problem. They said, everything is good, trust us. Of course, as researchers, we should not trust, right, in this case. So basically, we first did a device level study. We revisited it. And these are the key takeaways. We found out that basically we did an even larger study, more than 1,500 chips. We found out that newer DRAM chips are much more vulnerable to RowHammer. And there are some chips where you could induce bit flips after only 4,800 hammers, double-sided. So it's really 9,600. And you can get RowHammer bit flips in more rows and farther away from the mid to row. And most importantly, existing mitigation mechanisms are not effective. Especially, for example, para. We believe that para was a good solution. But we tested it 6 years later, and we said it has higher overheads. Para was the still most promising solution here, but it had significant performance overheads. So we're going to talk about that. So we actually built a lot of infrastructure to enable this. I'm not going to talk about these infrastructures. We tested a lot of chips from different standards, different technologies, different years, different manufacturers, as you can see. And this is one key takeaway, for example. So if you look at the DDR4 old curve and DDR4 new curve, this is the hammer count needed to induce the first bit flip, and this is the bit flip rate you get. So curve is shifting to the left and to the to upper. This means that you're getting more bit flips earlier, right, in the new technology. So that's one figure. This is another figure which shows that the first bit flips come earlier with the hammer count. So I'm not going to bore you with all of these details. You can read the paper, but basically things are getting much worse with technology scaling. And then we actually also, concurrently, we also wanted to check what's happening in real DRAM chips today. The DRAM manufacturers said they solved the problem. Did they really solve the problem? And basically, they were resorting to security by obscurity. And we showed that they didn't solve the problem completely. You could bypass all of these solutions. So this is the solution was called TRR in the industry. It's called target row refresh. And it's a general family of solutions. How it's implemented is up to the manufacturer, basically. So mitigations that are employed in the DRAM chips are not secure, as we showed. So the way we showed this was we did many-sided RowHammer, not just double-sided, but many-sided. And the idea is to hammer enough rows so that you could bypass the internal tables that target the rows and that count the access to the rows internally, that we hypothesized to be there internally. And we showed that basically, if you do this many-sided hammering, you could induce these bit flips. To be able to do that, we partially reverse engineered the mechanisms, not completely, but we reverse engineered enough that we would be able to induce these bit flips. And we provide an automatic fuzzing tool that can effectively create these many-sided RowHammer attacks. This is not a perfect tool. Later work, more recently, for example, Blacksmith from Kaveh Razavi's group improved this significantly. So this is an example of a many-sided pattern. So here you hammer 4 rows. And if you think about it, if there is a table that targets only 2 rows, you would overflow that table, right, internally. It's not as easy like that, but that's the idea. And you could see that these are the bit flips that we get after hammering 9 rows, we get some bit flips. After hammering 20 rows over here, we get some bit flips. So we didn't have a very good handle on exactly how this worked, but we had enough handle on overflowing these tables. And we were able to do 19-sided attacks and show bit flips. So in the end, we showed that 1/3 of the chips that we tested were we could induce bit flips, bypass the mechanisms, internal mechanisms. And we could also do this in real phones. And several different attacks were proposed using RowHammer. And you could basically get to the bit flips and do the attacks within a matter of seconds. It's not that difficult, essentially. So these are the key results. Again, I'm not going to go over that. Basically, these results were just scratching the surface, in my opinion. The tool was not exhaustive, and there was a lot of room for improving, for uncovering more vulnerable chips and phones. And later work actually did that. This is 2020 still. There's work in 2021, 2022 that actually showed that all chips can be bypassed. I'm going to mention one of them. So essentially what Trespass showed is that RowHammer is still an open problem, and security by obscurity is likely not a good solution. We should really be opening up and figuring out, proving the security properties of these chips. And if you want more detailed lectures, there's more. So essentially industry app solutions don't work. We also did some work on understanding, can we guarantee whether a chip is RowHammer free? I'm not going to talk about this, but I think it's a very difficult problem. How to test for RowHammer and how to guarantee a chip is RowHammer free. I don't know how to do it, basically. This is a paper we wrote about it. If you're interested in it, if you're interested in a challenge, feel free to look at it. But we also wanted to really reverse engineer what's going on in the chips. That's what this work is about. Essentially, I have this provocative title over here, industrial app solutions are very poor. I believe that. But the way we showed this was using our infrastructure. And we had all these questions clearly. How can we validate the security guarantees, etc. But we developed a more methodical approach to reverse engineer these chips. And here we have a methodology that leverages the data retention failures of DRAM chips. Remember those things we talked about earlier, to actually figure out whether a chip internally refreshed a row. So the idea is you profile, using our infrastructure, you profile which rows can retain data for how long, and then figure out some rows that are not supposed to retain data. But then you hammer some adjacent row. And if the chip internally refreshes the row that is not supposed to retain data, you would see that it's going to retain the data. So basically, you use the retention properties of a chip as a side channel to understand whether the chip is internally refreshing a row that's not supposed to retain data for that long. That's the idea. This is where RowHammer and retention actually comes nice, because if you didn't do all of those studies in retention, maybe we wouldn't come up with this insight. Right? And based on that, we were able to figure out what's going on internally inside the DRAM chips, because once you do that, you can figure out when a chip is internally refreshing which row, and based on that, you can figure out the internal mechanisms. And based on that, you can come up with new RowHammer access patterns. And based on that, we basically bypassed all of the protection mechanisms on all of the modules we tested. These are actually very heavy experiments using our infrastructure. And we show that more than 99.9% of the rows in a DRAM bank experience at least one RowHammer bit flip. You can get up to 7 RowHammer bit flips in this 8-byte data board, which is ECC is completely ineffective at this point. So the question is, how do you solve the problem? Again, I'm not going to go over this, but there's a methodology behind it. We actually open sourced this very recently. My student who did this work graduated very recently also. And this is our infrastructure. Let me show you some mechanisms from this table. So these are 3 major manufacturers, A, B, C. Basically, they all use different mechanisms. Some of them count the accesses. For example, this has this manufacturer uses 16 rows per bank. And this manufacturer uses sampling based, more like the para approach, for example. So their capacity is only 1. They're not per bank. This manufacturer used a mix of the mechanisms, both sampling based and count based mechanisms. So their mechanism is actually even harder to reverse engineer. So they all use different mechanisms in the field, but you can bypass all of them, as you can see over here, if you know enough. And this is showing. And I believe that we could actually understand even the last manufacturer more. It's a matter of time based. So we're only, let's say, 1-2 students dedicated over here. A much more powerful actor can do it much more easily, in my opinion. There's nothing hard here after you know what to do. Okay, so ECC is ineffective also. There's a lot more observation in the paper that I'm not going to talk about since we don't have a whole lot of time. But the reason why we do these studies, I believe, is this can help future solutions. If you can reverse engineer what's going on, you can help future solutions a lot. Okay, let me talk about some actually, are there any questions so far? Okay, please.
So is there a relation between memory clock rate and the ability to induce RowHammer bit flips? Because users can now overclock memory and consumer grade.
Yeah.
Right.
So memory clock rate really affects the bandwidth, the bus, essentially. It doesn't affect the internal operation. Yeah. So there's, as far as we know, there's no relationship between the bus clock rate and the internal operation. With voltage, that's a different issue. We will talk about that.
And we don't have any studies on GPU.
Yeah, that's a great question. Like GPU memory, GDDR or HBM. So we did not do those studies. We're building an HBM infrastructure, mainly because building this infrastructure is not easy. Actually, GDDR, HBM is very tough to get your hands on. We have an HBM-based infrastructure, so we're doing some studies on that. There's no reason to believe that they're not vulnerable. I believe they're vulnerable. Whether you can do these bit flips on GPUs is a different question. I think it's doable, but then you need to go through the software and hardware stack of the GPU to induce these bit flips, which is not as easily reverse engineerable, let's say. Yes.
So, what's the variation of that question?
Sure.
You already answered it. Right, when in those stack memories, actually, you have a third dimension.
Absolutely, yeah.
So do you think that's potentially significant?
So, yeah, that's a great question. I believe it will become significant if it's not significant today. Certainly, it's good to study it. So basically, I don't know the answer because we haven't done those studies. I believe it will have an effect. So for 3D, I have the answer for you for 3D NAND, and 3D NAND, it's absolutely significant. But 3D NAND has a different structure because you have the bit string 3D stacked, and really you have an effect. Whereas DRAM is you have different dies stacked together. Yes, there's some effect, but I don't expect it to be as high as it is in 3D NAND. But that's a great question. I think with future technologies, it could become even more significant, right? With more layering. And then there's a heat effect internally. So I think that needs to be studied more and scientifically completely. Yes.
Yeah, so I know you can bypass those industry solutions, but now if we need to do this like many-sided RowHammer attacks, does it make like attacks and practice more difficult?
Yeah, so that's a great question also. In a sense, yes. But again, if someone puts enough effort, I believe they can do it. So there's work from Kaveh Razavi's group at ETH who have shown that with Blacksmith, there's a work called Blacksmith and Smash. You could actually do this on JavaScript again, even on TRR protected chips using the insights that we have developed with Trespass, for example. So it makes it harder, yes. And I believe it also makes the benign applications a lot harder to induce bit flips. So it especially protects against benign applications. But from a security perspective, I think you're not fully secure. So someone can do it, right? Someone motivated enough can do it. Okay, great questions. Now let me talk about new RowHammer characteristics. So we also wanted to understand different dimensions of RowHammer. So we did even more intensive studies with our infrastructure. And we wanted to study effect of temperature, aggressor row active time, and victim DRAM cells physical location. So what is the spatial variation? So why did we do these studies? The main reason is, first of all, there's a scientific understanding aspect. We want to really understand what's going on, hopefully. But there's also, these affect the attacker and the defender as well. Maybe you can come up with better attacks and better defenses if you understand things better. Right? And I will show you some examples. And there's ongoing work actually to take advantage of this even better. So we built more infrastructure, let's say, so that we could actually control the temperature very precisely and voltage later on, as I will show you. We were able to test even fewer DRAM chips because these experiments take a really long time. So we have some takeaways. I'm not going to go over all of them, but for example, a RowHammer bit flip is more likely to occur in a bounded range of temperature. So between 80 to 85 degrees, some cells fail. Some other cells fail between 50 to 60 degrees. We don't know the exact effects over here. This is very interesting. We're trying to figure out. There are some hypotheses that we have in the paper. But basically, temperature has a correlation with the bit flips. The second one is, and it's not a straightforward correlation. It doesn't say that as you increase the temperature, RowHammer bit flips increase. That's not the case, no. The second observation is that if the aggressor is kept active for a longer time, you get more bit flips. So activating as fast as possible is not the way to induce more bit flips. You activate, wait for some time, and then activate again, and wait for some time. This builds up some charge. There's again some hypothesis over here, builds up some charge and leads to even more bit flips. This is fascinating, I think. The third one is maybe obvious, well, maybe expected to be obvious if you know about physical variation. There are certain physical regions of DRAM that are much more vulnerable. So based on this, we actually showed how you can craft more effective attacks and design more efficient and effective defenses. I'm not going to talk about this one. You can read the paper. Let me see. Yeah, we don't have a lot of time, so I'm going to skip this one. But basically, if you understand these observations, you see that keeping the aggressor rows active for a longer time can induce bit flips earlier, for example. And if your defenses are not designed to take this into account, you're vulnerable. This is interesting. I'll show you spatial variation over here. This is for manufacturer C, for example. The y-axis is the minimum number of activation count to observe a bit flip, and the x-axis is the sorted DRAM rows. You can see that some rows are not that vulnerable. Some rows are extremely vulnerable. This is orders of magnitude over here in terms of the number of activations. And these are different modules over here. So basically, there's a huge variation in terms of vulnerability. And that's true for columns as well. Again, I'm not going to bore you with each individual graph over here. There's a huge variation in terms of vulnerability of columns. Now, what can you do about this? So if you know this profile, you could make your solutions much more effective. So instead of protecting all of DRAM by the same amount, you could protect the most vulnerable part very aggressively and less vulnerable part less aggressively. And we showed that actually the solutions can be much more less hardware intensive if you actually apply this observation. I'm going to talk about the RowHammer solution a little bit, but there have been a lot of solutions also that were published in 2020, 2022. All of them suffer from some hardware overhead. Para is very nice because it doesn't have any hardware overhead almost, but these have hardware overhead if you want to really catch every single row. So this is actually not easier said than done, of course, right? Because how do you track the vulnerability of all of the rows in the DRAM becomes a difficult question, right? So this is not a practical solution at this point, but it can, by leveraging these insights, you could build better solutions over time. I'm going to ignore the temperature. This is even less practical, if you will. But I think these studies need to be done to build understanding so that you can do better in the future. Now, we did a little bit more RowHammer analysis. We, for example, looked at the word line voltage and its effect on bit flips, because RowHammer is really a voltage problem. You activate the word line with voltage. If that voltage level is very high, you're inducing more disturbance in adjacent rows. So if you reduce that voltage level, we did a lot of studies with this new infrastructure, let's say. If you reduce that voltage level, you can actually reduce RowHammer vulnerability. Unfortunately, it's not always desirable because reducing the voltage increases your activation latency as well as data retention time. So it's a trade-off, basically. And this is a trade-off that you get into when you're designing DRAM. But we showed that you could actually get to a better trade-off space where RowHammer vulnerability is a little bit better. And these are not that bad, let's say, in general. But I don't think this is a solution. It's good to build understanding, but I don't believe that this is a solution. Now let's talk about solutions. I believe solution really needs to be at the system level. It's unless DRAM manufacturers at some point come up with a new technology in DRAM, which is looking almost close to impossible today, the solution needs to be at the system level. And memory controller in particular, in cooperation with other parts of the system. So I'm going to talk about the solution that we developed, RowHammer. Again, I don't believe that this is the solution, but it could be part of the solution space. So let me cover the solution space first. So the first solution space over here is, I don't think it's feasible currently, and maybe not a good idea. Increasing refresh rate is not a good idea. Physical isolation, you mentioned the OS space, for example. I don't believe that that's a good idea in terms of wasting space. I think the main solution space is over here. Reactive refresh, figure out which rows are being hammered and refresh potential victim rows so that they don't lose charge. Or figure out which rows are being hammered and throttle access to them so that they're not hammered more until the DRAM area gets refreshed. That's the idea. So these two can be combined. So people have been looking at reactive refresh. Para is actually an example of reactive refresh without having access counters, right? All of these solutions trade off between cost, power, performance, complexity. And we've been exploring the space collectively, let's say, in the community. Our goal with the RowHammer work was to tackle the scaling challenge because RowHammer vulnerability is getting much worse while remaining compatible with commodity DRAM chips. We didn't want any changes to the DRAM chips or any information required from the DRAM chips. So the difference between these two approaches, reactive refresh requires you to know which aggressor row is adjacent to which victim row. So you need some information from the DRAM chip or have a way of completely reverse engineering it, which is not easy in the end. We wanted to get rid of that. So that's why we took the proactive throttling approach. So the idea is this basically, that's the goal, sorry. Efficiently and scalably prevent RowHammer without knowledge or modification to DRAM internals. And the idea is to selectively throttle memory access that may cause RowHammer flips. At the high level, we use area efficient bloom filters at the memory controller and detect a RowHammer attack and selectively throttle accesses to that particular row that you're activating so that that row doesn't get activated in a way that ensures that you don't get any bit flips. So you need to set some parameters so that you don't get any bit flips. And this requires, of course, your knowledge about when do you get bit flips based on the DRAM chip. I think all of the solutions we have today require that. So bit flips do not occur, and optionally, we said that you can inform the system software about the attack. So for example, you figured out that somebody is doing the RowHammer attack. We have this RowHammer likelihood index associated with a thread, and that thread is, let's say, marked, and that thread can be passed to the system software, and the system software can deal with it in some way. So I don't think throttling always is a solution in the end. Pass it to the system software so that you can do more analysis, or system software can do something else, right? So that's the idea. And the good thing is this is compatible with commodity DRAM chips. No need for proprietary information and modification to the DRAM chips. I'm not going to go into a whole lot of detail of how this works, but you need Bloom filters. You need to design them carefully, which leads to hardware overhead. And the key is no row can be activated at a high enough rate to induce bit flips. And the attack throttle identifies a RowHammer attack, essentially. And it greatly reduces the performance degradation and energy wasted of a RowHammer attack. And we will see that in the results. So we evaluated many other mechanisms that were proposed also in terms of many things, as you can see over here. So the takeaway is performance energy overheads remain negligible as you go down to a threshold of 1K, 1,000 activations leading to bit flips, when no RowHammer attack is present. You can see that our original solution, Para, is not doing well at 1K because it's refreshing a lot, basically. Some other solutions that were proposed by other folks in the community are doing quite well, actually, as good as BlockHammer. Where BlockHammer is good is, let's say, when it detects a RowHammer attack, it throttles it. As a result, performance of other applications, benign applications, increase, and the system energy also becomes much better. And then once you report to the operating system, hopefully, things will be even better. So basically, these are the key takeaways. What I didn't show you over here was better hardware area scaling. Hardware area is still high, but it scales better than some other techniques. I think still it's not good enough. Basically, we need to do more work in this area to make these solutions even more efficient going into the future. And we have a security proof in the paper, and we address a bunch of many-side attacks. And if you're interested in this, actually, we open sourced this recently, along with 6 other RowHammer protection mechanisms. So if you want to do research on RowHammer, it's a good place to start, if you will. And clearly, there are many dimensions of different protection mechanisms that I don't think we should go over right now. Okay, there's more in the paper, and you can take a look. And this is the GitHub where we open sourced. So I think this is an example of what I mentioned earlier, right? You need intelligent controllers for security, safety, reliability, and scaling. I actually strongly believe that this is true for many issues based on our experience. For example, the refresh, going back to the refresh picture that I showed you earlier, it needs an intelligent controller to determine which rows need to be refreshed at what frequency. And then you can use this information either at the control level or pass it to the operating system or some application, if you will, and they can take some actions in terms of refresh. So I believe refresh and RowHammer both require intelligent controls and other issues as well. Now there's more on RowHammer. It's fascinating. I think I learned about some more papers when I was attending Micro that I missed apparently in 2020. But there's a lot of work going on in security sessions and architecture conferences. There was a session on IEEE security and privacy on RowHammer alone, if you will. It's quite interesting, I think. I don't have time to talk about that. And people are actually trying to rethink some of the RowHammer mitigations. They're actually very, very interesting papers. So this is the paper that I mentioned earlier that does these attacks, RowHammer attacks through JavaScript on DDR4 chips, supposedly protected chips. There's more. Actually, this year's IEEE Symposium on Security Privacy had also 4 papers. One of them was interesting. They were able to extract model parameters, model weights, deep neural network weights, actually using RowHammer. I think they called Hammer something, but I don't remember. So you may know it better than I do. Yeah, there are other mitigations also. People try to, for example, randomly swap rows to mitigate RowHammer. So if you see that an attack is happening, why don't you randomly swap some rows? This is interesting, I think, assuming you can mitigate some of the overheads of randomly swapping. We actually also have a similar solution, but we have some DRAM support. We need to change the DRAM so that swapping the rows is easier inside the DRAM. I have some of my doubts about the overheads of all of these solutions, clearly. But sometimes some of these solutions may be needed, especially in the future when the RowHammer threshold becomes very small. So imagine a world where you get a bit flip after 64 activations. Some benign applications actually do that easily today. Some of these solutions have their place, I believe, actually. Then the row swapping becomes very interesting, in my opinion. Okay, there's more that I don't have. So this is actually an interesting paper that from Microsoft that talks about we need to be more open about what's going on inside the DRAM and expose it to the system so that we can develop better defenses at the higher levels of the stack. I strongly agree with this, actually. We have a position paper on this also that I'm going to mention briefly. Google also developed this attack called half double. I think it's quite interesting. And there's more. Okay. So let me talk about some of the things. So this has appeared at Micro, actually. We actually have been looking at refresh and RowHammer. So we were able to show that in real DRAM chips, you can overlap some of the refreshes by violating the timing parameters. You can overlap a refresh to one row in one subarray to a refresh to another row in another subarray. And you could actually do this. To mitigate the overheads of some of the RowHammer mitigations. And this is very interesting. I think you can do this in real DRAM chips today in a limited manner. This is where we propose that I think the real solutions will become much better if DRAM manufacturers provide a little more information to the higher levels of the stack. For example, at least the row mapping information. And we argue for that over here. And there's more to provide. I will mention one solution. This is on archive. I believe this is a step in the right direction, and there needs to be more things to be done over here. So the idea is self-managing DRAM. One of the issues in RowHammer refresh, even with memory scrubbing, is DRAM doesn't have time to do these mitigations. We call these maintenance operations. So why not give some time to DRAM to do these operations? Don't implement them in the memory controller, but let the DRAM manufacturers deal with it. And have an interface that allows the DRAM to have some breathing room. Today, we don't have any breathing room in DRAM. Memory controller dictates everything, and the DRAM is supposed to respond, right? And that's the idea over here. DRAM has some autonomy, not a whole lot, but it can reject the row activation command. It can say, I cannot service your activation right now because I'm doing a RowHammer preventive operation in this particular region of DRAM, or I'm doing some refresh, something smart about refresh. And I believe this is good because this gives the DRAM manufacturer, and I believe DRAM manufacturers are still the people who know the most about what happens inside the DRAM, and they can mitigate these things internally without running into security problems. And that's the idea. This requires, of course, some change to the interface. This requires another pin from the DRAM chip and change to the interface. I believe those interface changes can be discussed more. So this way, you can actually implement many different maintenance mechanisms. We looked at DRAM refresh. All of them become more efficient inside the DRAM. We looked at RowHammer protection. Again, all of them become more efficient inside the DRAM, and also memory scrubbing, which is important actually in large-scale systems especially. And that becomes more efficient inside the DRAM. So you could implement all of these. Normally, you lose performance, but we showed that with self-managing DRAM, you gain performance and energy efficiency by doing this internally inside the DRAM. Because you could actually do that at fine granularity, locking fine granularity regions, and you could actually do it very efficiently. The memory controller doesn't get tied up managing the DRAM as well. So that's the idea. I believe this opens some new thinking. So if you think about DRAM, at some point in the past, things were asynchronous, right? We had these asynchronous protocols. DRAM and the processor communicate asynchronously. We moved to the synchronous protocols where memory controller was in charge of everything in the end. We're bridging the gap between asynchrony and synchrony. We're still remaining mostly synchronous, but we're giving some breathing room, some asynchrony to the DRAM chip. So there's a lot of fascinating discussions over here. My PhD student, Hassan, developed this idea, and he recently gave his thesis talk. And this is a longer version of this talk, if you're interested. Okay, there's much more in our preprint. And there's more coming up in 2023 in RowHammer. I find this fascinating. So I believe there's more to come. Any questions before we start concluding? Yes, please.
Like protection, like for targeted protection, are you worried about the vulnerability regions would migrate or change over time, and then with the overhead, it's gonna get involved and figuring out changes? Like with the self-managing DRAM? Yeah. Mm-hmm. Welcome. Yeah, I mean, potentially, yes, you need to adapt to it. And there's some overhead potentially, depending on how you do the Bloom filters in RowHammer, for example. I think especially these sort of issues become worse as the RowHammer threshold reduces. So for example, RowHammer doesn't scale to 64 activations, unfortunately. We don't have any solution that scales to 64 activations today. So I think we need research, certainly, looking at those issues and other issues as well. Okay, so let me move on. Let me cover the high level very quickly, and then I will conclude. So I think future is going to be worse, basically. We're going to have more errors.
And if you say other memories are good, unfortunately, they're not. And some of them are, for example, Intel announced that phase change memory, they're not developing 3D exploit. That doesn't mean that other people not develop, but all memory technologies will have problems like this, in my opinion, as they scale to small technology. And I believe we need intelligent controls for all of them, frankly. So how do we deal with this? I believe we need to develop even more understanding. That's what we've been trying to do with RowHammer and Refresh, for example. Understanding is needed based on real device data analysis. These things are very difficult to model with simulation, actually. We tried to do it, others tried to do it. You cannot really model RowHammer with simulation as far as we know. So real device analysis is really important. Based on that, we need to develop reliable metrics. And also the principled architectures with good partitioning of duties across the stack, right? Right now, we have a terrible partitioning, in my opinion, between DRAM and the system. DRAM is like a dumb device that cannot do anything, right? As a result, I think, for example, we could discuss why DRAM manufacturers weren't able to protect DRAM, even though they have so much knowledge about DRAM. There are culture issues, of course, but culture issues aside, they have very limited breathing room, right? DRAM manufacturers cannot do much given the slack they have inside DRAM chips today. So we should really revisit how we partition the tasks across the system. But we cannot give up performance and efficiency, and we need patchability in the field. And design and testing is extremely important, I think. We need more online testing methods to discover these issues and protect these issues and make the solutions better over time. Yes?
Some might say that's not an architecture question, that's a business question.
Which one?
The partition we have.
So I think, I think that's absolutely true. But I think as you could take the researcher approach, say, this is a good partitioning, let someone figure out the business. Because if you go into business, I think nothing will change. So if you look at the JEDEC, it's very difficult to get anything to change, right? And that's one of the reasons actually why we propose a self-managing DRAM, because it enables some of the ideas to get adapted without changing the interface. You just need to move to this new interface, and then you can adopt some of the ideas more easily. But I agree. I mean, there is a huge business aspect of this also. Not, as far as I know, not like this, basically. This is a very simple, small change.
No, not exactly. Of course.
Yeah.
But basically, products that allow you to have self-managed DRAM.
Yeah.
And then people with low logic devices are not friendly.
Yeah, I think there needs to be some understanding of what is the protocol, right? I agree. So people, for example, who own the memory controller today, they don't want to give up the functionality. So scheduling of operations, for example, because they think they know the scheduler much better based on the application. I agree. There needs to be some rethinking of what should remain where. No question about that. I think, but I believe, for example, a Refresh, RowHammer, it's really the DRAM manufacturer, they know most about those issues internally. I don't think memory controller manufacturers, they can know about that, no question about that, by testing, by doing what we're doing, for example, but it's a lot of work for them to know about that. So that's, yeah. Okay, so I think there needs to be more over here. Okay, so these are the understanding. So let me go back to these bridges and then I'm going to conclude. So these bridges are interesting to me because they're bit flipped, right? And we keep getting bit flips, as you can see. And the most recent example, well, I'm not going to name this most recent, but one of the recent examples is here. Does anybody recognize where this is? Pittsburgh, yes. Maybe Yanjing went over that bridge. I went over this bridge many times. This is the Forbes Avenue Bridge. And yeah, you don't want to be in that bus at the time. But I think clearly we've been building bridges for thousands of years and we still haven't gotten it right. You could argue, okay, we don't do enough maintenance, blah, blah. We still haven't gotten it right. We're not going to get DRAM right also, in my opinion. That's why we need to somehow protect it, right? And I think we're much better at figuring out how to protect computers because computers are not like bridges, right? Bridges are heavy infrastructure, whereas computers were soft. We can introduce patchability. We can introduce basically more adaptive techniques. So I believe we're in a better place than bridges. So I'm going to go back to this paper. Yes, we do need to take a systems approach to this problem. So sometimes I get the question, oh, this is the DRAM manufacturer's problem. Why is anyone bothering with this? Actually, our first RowHammer paper was rejected partly because of that reason. This is the DRAM manufacturer's problem. Don't bother us architects about this, right? That was one of the things. I believe architects and the system designers need to be bothered. And industry is actually writing papers about it. This is a paper that was written by Samsung and Intel. Only paper that I know of that was written by Samsung and Intel together. And these folks actually, I know some of these folks personally, they've been working on DRAM for decades and decades. And they basically say we should co-architect DRAM and controllers together. Okay, let me give you some final thoughts. As I said, I was going to talk about earlier work, and this is actually a beautiful paper that was published in IEEE Security and Privacy in 2003. These folks from Princeton showed that you could induce bit flips in memory, and based on those bit flips, you could take over the Java virtual machine. I think this is a paper kind of ahead of its time. There were also earlier attacks on cryptography, for example, using fault attacks. Very interesting. But these folks actually physically injected faults. So the way they induced these bit flips were using this lamp that heated up memory, and you would get bit flips. This is nice, clearly. It's beautiful. It's a nice prototype, but it's not realistic, right? Well, at least not in very commonly realistic, let's say. Clearly, it's realistic because they could do it. So I think this paper is very interesting. I read this paper a lot earlier than I started doing RowHammer research. And I always thought, is there an easier way to induce bit flips? That's what RowHammer enabled, in my opinion. Basically, a simple error can be induced by software. And as a result, you see now the security community taking up this and developing a lot of fascinating attacks. Okay, I'm not going to go into a whole lot of this, but essentially we'll see more RowHammer attacks because the problem is still out there. Now the bar is higher because there are solutions implemented. However imperfect, there are solutions inside the DRAM chips, and people are going to strengthen those solutions. The bar is going to get even higher, but people are, I think, also quite creative. If the solutions are perfectly secure, they're going to find a way of overcoming those solutions. No question about that in my mind. I think maybe, I'm not going to say more importantly, I think we should be doing both attack research and solution research. And we should really be doing more solution research also. There's more to come. And we've seen even more solution research right now than in the past. Okay, I think more importantly, I think we should be thinking what else is lurking around, let's say in hardware. I think RowHammer showed that general purposes hardware is fallible in a widespread manner. Its problems are exploitable. And this mindset has enabled, I think, a lot of churn in the hardware security research. In fact, people are understanding hardware a lot more today in the security community. And folks who have developed Meltdown and Spectre worked on RowHammer heavily before. Some of them, not all of them, but some of them. So I think that's good. And we should be really poking into hardware and figuring out what else is there. What are the other RowHammers in the world? So let me conclude. I think memory reliability is reducing, and reliability issues open up security vulnerabilities. These are very hard to defend against, especially when they discovered in the field. Right? RowHammer is a prime example. As I said, I believe this is the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. I think its implications on system security research are tremendous and exciting, but I don't think it's just system security. It's also really architecture, reliability, dependability research. The bad news is RowHammer is getting worse, and it's going to not get better unless we somehow move to a new device. Good news is we have a lot more to do, and we know what to do, in my opinion, at least the directions we want to go through. We are now fully aware that hardware is easily fallible. We're developing both attacks and solutions. And hopefully, this is harder to do. More principled models, methodologies that will lead to even better solutions. And again, if you're interested, this is the retrospective, but as I said, this doesn't cover the works that was that I presented here since 2020, but there's a lot of work that was before 2020 that is covered here. It's a good entry into RowHammer, if you will. So for example, if you want to know about the device level reasons, we talk about some device level issues over here also, which I didn't. I drew an abstraction level. I said, I'm not going to go into what's going on in the device level. That's also fascinating. Okay, so I will thank people who funded us. And most importantly, I'll thank people who've done the research, since clearly I didn't do those experiments. I've looked at them, but I haven't done them. And this is some of the faces that have contributed to it. If you're interested, you can read the newsletter. And if you're interested, you can also attend our lectures, as was mentioned earlier. I'm a YouTuber, but it's not just for that, because we actually get a lot of interesting participation online as well. And we also have, if you're interested in doing research in this area, we also have these special courses where we talk about the soft MC infrastructure. And you can jumpstart, if you will, by learning about the soft MC infrastructure, and also a Remulator, which is a simulator that we've developed that can enable you to do some of the RowHammer solution studies, for example, because you need to modify hardware if you are developing a hardware solution, and you need to test that somehow. And simulators like Remulator enable that testing easily. And the infrastructures that we open source are all based on Remulator. For example, the BlockHammer solution infrastructure that has 6 other solutions together that are open sourced are based on Remulator. Okay, with that, I'm happy to take more questions. Thank you. Yes, please.
So the solution you're proposing looks a lot like what storage has been doing with SSD. And so the fact that you have to have intelligent control on SSDs to do things like layer leveling.
Mhm.
So
Yeah.
are there lessons we can learn from them?
Yeah.
Memory controllers, or do you think that they're fundamentally so different that
Mhm.
it might be difficult to achieve that?
Yeah, that's a great question. I think yes, I think at a high level, exactly, SSDs are doing that, right? Because if you look at flash memory, for example, it's a memory that doesn't work off the bat. You have to have an intelligent controller to make it work, and that's what we're doing over there. That's why I flashed some of the slides earlier on SSDs. I think we can learn some of the lessons, no question about that. We need to be a bit careful because the time that you have to correct errors, for example, in SSD is very long, right? In DRAM, you don't have time. Otherwise, you waste the technology, if you will. So we need to be a lot more agile in DRAM. And we need to adapt to the error characteristics. For example, read disturb exists in SSDs and there are mitigation mechanisms, but it's a different sort of read disturb, right? For example, when you read a block, a page in an SSD, you disturb all of the other pages in the block. You apply actually even higher voltage to those pages. As a result, everything gets disturbed. So you need to be even more careful, even more aggressive in SSD. But throttling, a general approach, throttling is one solution. Remapping of data is employed by SSD is another solution. So some of the solution ideas can be applied, but they need to be applied in the context of DRAM, where the trade-offs are different.
The tight timing and the fact that there's a common clock between, or like it's synchronous, right?
Yeah, exactly. Synchrony. Yeah. Yes, please.
So a lot of this comes from unified vision of memory, right? So we live in this world where one human is king and everything is trying to target the same memory, and virtual memory pretty much facilitates that. Is there room for other more segmented ways of looking at memory that could lead to better improvements in security as well?
Yeah. So basically, I think if I understand you correctly, somehow change the isolation model so that things are separated from each other and they don't affect each other through RowHammer.
Right.
I think that's, I mean, I don't know how to do this at this point, but certainly it's good to look at them at the system level. I personally don't believe virtual memory is actually the way it has been designed and used for more than 60 years is the best approach to security or even managing memory. So we should really be looking at those things. And that could solve some of the things into application. But in the end, somehow you have to share, in my opinion. Once you go into those shared parts of memory, then you will run into these issues. No question about that. I don't feel that will be a complete solution to RowHammer. RowHammer, in my opinion, should be solved completely in some way, but not with better isolation mechanisms at the system level. That will mitigate the effects of RowHammer underlying, but can it eliminate all of the effects? I'm not sure, frankly. And there's also the other aspect. This is not just an inter-application problem, right? Inter-address space problem. Within your own address space, you can cause problems also. You can leak private data, for example. Rambly work showed that. You can also steal weights potentially somehow, or you can actually get bit flips and neural network accelerators potentially. Yeah. That's a very good question, though. I think that runs into some other research that we're doing on rethinking virtual memory. And that should be done, no question about that.
Now let's
Hey, thank you.